Hey folks, a very good evening and thank you for joining in today. Could you please confirm in the chat window? I have it open on my phone. Could you please confirm if you're able to see the screen and if you're able to hear my voice clearly? We'll get started in just a couple of minutes. So could you confirm in the chat window if everything is as expected? Okay, cool. Thank you. Thank you, folks. Yeah. So the mentors also have joined the chat window. Cool. So it seems like no glitches whatsoever. So we'll get started at 7 p.m. sharp, right? We have a couple of more minutes. So we'll get started as soon as the clock ticks 7. Again, just a quick reminder, we have a live session tomorrow for general Q&A. Again, please understand that in a public Q&A, it's almost impossible to answer all the questions. So we'll try to answer as many questions as we can in tomorrow's session. So it also starts from 7 p.m. It's a 1-hour session and please keep your questions ready and we'll try to answer as many as possible. And we'll try to answer a wide spectrum of answers, or we'll try to answer a wide spectrum of questions. Instead of repeating the same answer or instead of answering the same type of question, we'll answer a broader spectrum of questions tomorrow. Okay. So again, this was primarily students' request. So we thought at this point of time, it's a good idea to have a general live session also. It's general Q&A, nothing technical. Cool. Yeah. So we have 1 more minute. We'll get started as soon as the clock ticks 7 p.m. Again, as you can see on the screen, today's topics are combinatorial circuits and sequential circuits and counters. So I hope you have revised these concepts. Okay. So Ramakrishna says that our test series is hard compared to others. Probably others are giving too trivial questions. We prepare students even for a hard gate paper. We mostly focus on gate level questions, number 1. A vast majority of our questions are gate level. A small percentage of our questions are slightly harder than gate questions, and that's by design. Because in case the gate examination is harder, it's better to prepare for a harder exam, because makes logical sense, right? Than to prepare for a lower than harder question paper. So that's why some of our practice tests, some of our test series questions, most of them, almost 90+% of them, almost 95% of them are very typical of what you can expect in gate. A few easy problems, a lot of medium hardness problems, but there are some which are slightly above the gate level, and that's by design. We intend to keep the test series quality very high so that you're better prepared for these, for the actual gate exam, right? Even if it is slightly harder. Somebody says, please update the compiler design as per the new gate syllabus. We are recording compiler design now. As soon as we have, as soon as we update the compiler design videos, maybe in a day or 2, we will surely update the notes also. Okay. Cool. Sounds good. So let's get started. 7:01. So let's get started with the questions today. Again, as usual, we'll start with some easy questions, then move on to some medium level questions. Cool. Okay. Please focus on solving these problems. Tomorrow, anyway, we have a general Q&A session where we'll answer general questions for sure. Today, it's better to focus on solving the digital logic design questions. I'll try to answer a few general questions in between if time permits. Again, we are intentionally starting with a few easy problems so that you get warmed up. So at least the first few questions you should be able to easily solve. Think of them as a quick revision, or again, you can expect some questions like these for 1 mark in gate. Again, these are easy by gate standard. Okay, I see people putting in the answer. Fairly straightforward questions initially. If you know what is a multiplexer, And if you know how to write the equation of the output of a multiplexer, this is straightforward. Good, good, good. I see a lot of students putting in the answers. Good job. Good, good, good. Okay, most of you got it right. The option 3 is the right option, and it's very simple. For those of you who may have forgotten this, as a quick recap, look at this. What is your y? When a equals to 0, b equals to 0, 1 will be your output. That's how a multiplexer works, right? So a dash, so when a equals to 0 and b equals to 0, the output is 1. So a dash, b dash 1, plus when a equals to 0, b equals to 1, right? So when a equals to 0 and b equals to 1, what is the output? The output will be c, right? Simple. Next, when a equals to 1, b equals to 0. Okay, a equals to 1, b equals to 0, the output will be 0. So multiplied by 0. Plus, when a equals to 1, b equals to 1, the output will be c, right? Because this corresponds to 1, 1, this corresponds to 1, 0, 0, 1, 0, 0. Typical, this is a standard multiplexer here, right? So let's simplify this now. So this is a complement, b complement, plus this is anyway 0 because it's a product with 0. Then if you look at both of these, you can write it as bc, a plus a complement. Just simple distributive law. A plus a complement is 1. 1 multiplied by anything is itself. So what do you have? You have a complement, b complement plus bc, which is nothing but your option 3. So this is a very, very simple, straightforward problem. If you know how a multiplexer works, it's trivial to solve it. Okay, cool. Let's go to the next problem now. Again, this is also a very simple question about multiplexers. Okay, here comes the second question. Again, an easy question. The first few questions are easy intentionally. This function is just testing if you know how to implement how to use multiplexers to implement Boolean functions. Again, please read the question carefully. Some of you are doing a silly mistake, so please read the question carefully. It says without using any additional gates. That's important. It was a fairly easy question. There are a few slightly lengthier questions that we will deal with little later. This is fairly straightforward. If you know how to implement Boolean functions using multiplexers. Again, most of you got it right, but some of you got it incorrect. The answer is 16 cross 1 multiplexer. Because look at this, if you have 4 variables, imagine this is a multiplexer that you have, right? You have 4 variables, right? So you have, think of them as your select lines, right? These are your select lines. So how many inputs can you have if you have 4 select lines? Because you have 4 variables, let's assume the variables are A, B, C, D, right? So you will have 16, look at this, you will have 16 input lines, and you will have one output line. Let's just say I0 to I15, right? So you can implement this function. So if this is your multiplexer, look at this, if this is your multiplexer, now all of the minterms that you can construct with A, B, C, D, all of the minterms that you can construct, look at this, this will correspond to minterm 0, this will correspond to minterm 1, this will correspond to minterm 2, so on and so forth up to minterm 15. Now given any Boolean function of 4 variables, right, you can write it using SOP. You can write it using SOP, and what will this contain? This will contain it could contain anything from minterm 0 to minterm 15. It could contain any of these minterms, right? So whatever minterms you have, whatever minterms you want to be part of this, right, you can just activate those inputs and you're done. So some of you got confused and said 4x1 multiplexer. Remember that 4x1 multiplexer has 4 inputs. So that's why it's important to draw the diagram. 4x1 multiplexer has 4 inputs, 2 select lines. So these are your inputs, I, J's. It has 1 output and 2 select lines, right? Because you have only 2 select lines, right? You can only create all the functions with 2 variables, not with 4 variables. I think that's a common confusion that students do run into, right? So the question here is 4. So it says, so somebody says 4 variable. Yes, if you have 4 variable multiplexer, if you want to implement a 4 variable function without using any additional gates, the 4 variables will be given as 4 input lines here, right? So that's the key here. So 16x1 is the right answer here. Again, it's very easy to get confused because some books write it as 2x4 multiplied by 1 multiplexer. Okay, so some books also write it. So the correct way of, again, 2 power 4 is nothing but 16. So it's very easy to get confused with this, but A is the right answer here. Cool. Okay, let's go with the next question. Again, somebody is saying what happens if other gates are allowed. Again, that's something that we solve in our course videos. We solve how to design circuits with n variables using a smaller multiplexer using additional gates. Okay, in this we don't have that question, but we have solved similar questions in our course videos. Cool. So let's answer this. This is also an easy question. It might look a little intimidating, but if you can understand what a decoder does, if you can understand the logic, it's fairly straightforward question. Again, here note that E is the enable pin, if somebody doesn't know that. Again, this is fairly simple. Just follow the logic carefully and you'll get it. Again, please think through this carefully. Again, Mayank says digital logic, lot of content for 3-4 marks. It's actually not 3 to 4 marks. On an average, you can get about 6 to 7 marks. I mean, 5 to 7 to be more precise. But DLD is very scoring. It's like somebody giving you like 6-7 marks trivially. Even if you know the basic concepts, the questions are typically easier. So just make sure that you know the concepts and it's very quick to solve. I see people putting in the answers. Okay, let's see. Again, please read the question carefully. So DLD is very easy to score marks in. If you know some basic concepts here, it will help you enormously. Again, some of these concepts are also used in computer organization. So you can score marks in COA also if you know some of these concepts about decoders and multiplexers in digital logic design. Okay, I see people putting in A, B, C, all 3 options. So please check your answers, folks. This problem, it's very easy to do silly mistakes if you're not careful. This is an easy question, but it's also very easy to make silly mistakes on. E stands for the enable gate. Don't forget that. Or the enable input, I'm sorry. Again, I see a lot of students doing silly mistakes here, so please look into it. Please read the question carefully. This is an easy problem, but also very easy to make silly mistakes on. Okay, just in the interest of time, because we have 10 questions, let me try to answer this. Look at this. We want this f to be 1, right? When will this f be 1? That's a question, right? For how many addresses? Your address is A0, A1, A2, A3, A4. That's your addresses, right? So for how many addresses the function f is equal to 1? Look at this. So if you look at this, this is 2 input, the 2 cross 4 decoder. So when will this output be 1? When this is equals to 1 and this is equals to 1. And when the chip itself is enabled. If the chip is not enabled, makes no sense, right? So this chip has to be enabled. When will this chip be enabled? If you give 0 input, because there is E bar here, if you notice, right? There is E bar here, which means this chip will be active only when this input here is 0. Okay, only then this chip will be active. So for getting f equals to 1, your A0 should be 1, your A1 should be 1, and this should be 0. And when will this be 0? Look at this. When will this be 0? First and foremost, this chip is always enabled because the input is 1 and this is E itself. This is not E bar, right? Which means this chip is always enabled. Now, look at this. If this chip is enabled, suppose if you give, let's just say, so this is 0, 1, 2, 3, 4, 5. So this is the fifth output, 6, 7, right? So this is 0, 1, 2. That's how I'm counting this, right? 3, 4. So the fifth output, look at this. This output will be high when this is 1, 0, 1, right? When it is 1, 0, 1, this pin will be high. But when this pin is high, this whole circuit is deactivated. So we want this to be low. Remember, we want this to be low. So when will this pin be low? This pin will be low or 0, except when the input is 1, 0, 1. For all possible, see, look at this, A2, A3, A4, there are 2 power 3 possibilities. So there are 8 possibilities, right? Because there are 3 Boolean variables, there are 8 possibilities. Amongst these 8 possibilities, except this one possibility, right? When A2 is 1, A3 is 0, A4 is 1, in this exact instance, your 5 will be high, except in this case, except for this possible combination of A2, A3, A4. In every other combination, this output will be 0. So which means 8 minus 1, there are 7 combinations. Look at this. Remember, A0, A1 has to be 1, 1. But when it comes to A2, A3, A4, there are 7 combinations which will lead this output to be 0. This is anyway 1. So this f will be equal to 1. Right? So the right answer here is C. I think some of you misread the question. Okay, or some of you did not. So some of you have answered A. The 2 most popular answers I see are C and A. Right? So because there is C and A, the biggest problem here is if you don't see this carefully, if you don't make a note of this, it's going to go crazy. Okay. So some of you are saying, please zoom in. I'll do that. I'll try to do that. I think there is a limit on how much I will be able to do it. Let me see. Yeah, I think this is the max. Again, zooming in. Okay, 1 second. Let me see if I can. I want everybody to be able to see the question also. Okay. So yeah, this is my max zoom. I think going anything beyond this, you'll not be able to see the whole question. Okay. So yeah, so this is where we are. Again, somebody says, Nihal says, if the complement was not there, the answer is A, but that's not the question, right? So it's a very common silly mistake to commit. So you have to look whether something is, something has a complement or not very, very carefully when you're solving circuits like this. Cool. Okay, here comes another easy question about multiplexers. Again, this is a 4x1 multiplexer. The output is F. Okay, there is this arrow missing here, but let me just draw it for you. This output is F. Very simple question. Yes, Mayank, I think we mentioned this yesterday also. The questions that we are doing in these live sessions only for digital logic design, not for any other subject, only for digital logic design, because we read the whole content. These are from the practice test. These are some of the practice test questions. Yes, I mentioned this yesterday also in yesterday's session. Except for digital logic design, for all other subjects, we created questions from scratch. These are not the practice test questions for other subjects. Only for DLD, because we read the content, we thought we'll do some practice session questions here. Again, practice session has almost double or sometimes even more than double the questions that we see here. This is a very simple question. Again, some of these easy questions are for you to get a good quick revision of the concept. Again, we have some medium problems later. Don't worry, we'll see more exciting questions a little later. Okay, I think most of you got it right. The option 4 is the right option. Very good. So let's actually write it down for those of you who may be a little struggling to figure this out. Look at this. When these two are 0, right? So A complement, B complement, then I0 is selected. So you get C as the output. Right? That's what F equals to. So F is equals to this. Now at the same time, when it is 0, 1, okay, when A is 0, which means A complement, and B is 1, which means B, so 0, 1, you select I1. I1 is also equals to C. So write C here, right? Plus, when this is 1, 0, which means A, B complement, then you select I2, right? 1, 0. Those are select lines, right? So you get C dash, which means C complement, right? Then when both of them are 1, again you get C dash. Now you just have to simplify this. So if you just look at this, you can take A dash common here. So if you take A dash common, what do you have? B dash C and BC. That can be written as C into B plus B dash, right? And we know that B plus B dash is 1, C into 1 is C. So this whole thing is nothing but A dash C. So these two it's simplified. Now what about these two? Let's write that down. Similarly, here we can take A common. Okay, yeah, we can take A common. We can also take C dash common here, right? So you get B plus B dash, right? So B plus B dash is 1. C dash into 1 is C dash. So A into C dash is plus AC dash. Now this is the standard formula for your XOR, right? So this is nothing but A XOR C. Very simple question. Okay, cool. So let's move to slightly more interesting questions. Very simple question. Okay, here comes the next question. Mayank, please remember that this is the first session on digital logic design, right? So we will surely cover more harder problems in the next iterations of this subject. Remember, this is the first iteration. It's very easy for us to create hard questions that 99% of students won't solve. Our objective here is to help students quickly revise the concepts, because I can give 10 hard questions. That's very easy for us, right? Our objective is not to do harder questions. Since this is the first iteration, we want it to be a quick revision with a few easy questions, few medium problem questions, and surely we'll go, as you come closer to the exam, we'll mostly do medium and a few hard questions. Okay, so don't worry about that. This is like a quick revision session. We have a few good questions on flip-flops, so don't worry about it. Again, we are trying to accommodate everyone into this ecosystem, where there will be a few medium problems, few easy problems, so that people don't get demotivated, right? So we are trying to balance these things out. Somebody says master slave is not in syllabus. Again, it's not mentioned that it's there or not there. Race condition or race around condition type of stuff is asked. If that is there, master slave should be there, logically speaking. Or did I give something wrong here? Aha. Okay, so both B and D are the same options. Okay, sorry, I think, okay, fine. Let's keep it as is. Okay. Sorry, I think when we wrote some of these options, we wrote them incorrectly. Yeah. So option B and D are one and the same. So if B is the right answer, D also logically is the right answer. Again, the future iterations of some of these subjects will be publicly available, but a vast majority of them will be privately available only to our course enrolled students. I think we've mentioned this from day 0 onwards. From the time we announced these live sessions, we mentioned it very transparently and clearly from day 0. Palash has a question, which is if he starts preparing from 1st of September and puts in 8 hours a day, can he get under 1,000 rank? Yes, very possible, Palash. We have seen students who got even double-digit ranks or low triple-digit ranks, below 200 rank last year. People who started their preparation in September, but they were very, very disciplined with their preparation. So you have to be disciplined with your preparation to get a good to get a good rank. It is possible. Yes, it is very possible. 8 hours a day is pretty good. Okay, I see people putting in the answers. I'll wait for a few more seconds. Let more people just think about these options. This is, even though we call it medium because it requires multiple concepts to be known, it's a fairly straightforward question. Which are the correct statements, right? Yeah, so that's the question. So somebody is asking, will these questions be available in the website as PDF? No, sorry. These videos will be available for the course registered students also as part of the course videos. We don't give partial access to our course videos, unfortunately. Sorry. You can watch the free videos because we publicly put them out for everyone's benefit. Cool. Let's answer this, right? So consider the following statements. A flip-flop is used to store 1 bit of information. Common sense. If you know what a flip-flop is, yes, the answer is right. Race around condition occurs in a JK flip-flop when both inputs are 1. So in a JK flip-flop, what happens? You have J, you have K, you could have a clock here, you will have Q and Q dash, right? So when J equals to K equals to 1, what happens? This starts behaving like a toggling system, right? When this happens, what happens? Q next equals to Q dash, right? It behaves like a toggle gate, right? Oh, sorry, it behaves like a toggle flip-flop, I'm sorry. It behaves like a T flip-flop. When toggling happens, when something like this happens, it is possible to get into a race around condition, right? So a race around condition happens in a T flip-flop because it keeps toggling the output, right? So yes, so race around condition occurs in a JK flip-flop when both inputs are 1. Yes, so this is also a right option. Master-slave configuration is used in flip-flops to store 2 bits of information. No, master-slave configuration is a solution to the race around problem that you encounter in when you have a toggling like flip-flop, like JK with both inputs 1 or T flip-flop with T equals to 1, right? So this statement is not true, right? Because master-slave configuration also stores only 1 bit of information. It uses 2 flip-flops typically, primarily to get around the race around condition, right? So that's the objective. So this option is incorrect. A transparent latch consists of D-type flip-flop. Again, what does a D-type flip-flop do? Your Qn equals to whatever input you have at this time. So whatever input you have becomes the output. Your Q next is nothing but D. So this is behaving like a transparent latch. Okay, so whatever you're sending as input is coming out, which means it's working like a transparent latch. Okay, whatever you send, you get it out. So this is also true. So 1, 2, and 4. So option C is the right option here. Right. So that's how you can look at it. Right. Cool. So let's go to another question now. This is an interesting question. This is a question in the intersection of digital logic design and counting and combinatorics. Again, all questions about course registration, please reach out to us at gate.appliedcourse.com. Our team will be able to help you. Because I don't want to talk too much about it here because we want to solve problems. Again, this is an interesting question. Again, it's a question where you can easily do silly mistakes. So please focus on the question here. We have a general live session tomorrow where we'll try to answer as many questions as we can of yours. This is a interesting but slightly tricky question. This is a question in the intersection of digital logic design and combinatorics. You'll see some of these types of questions in GATE also. Okay, I see people putting in the answers. Again, this is actually easy, but we just thought we'll put it medium because I like problems which are in the intersection of multiple subjects personally. Even our team loves them because that's a great way to ask questions by mixing up concepts from multiple subjects sometimes. And these types of questions are often asked in GATE also. Okay, thankfully many of you got it right. The answer is, okay, let me solve the problem for you while others are also solving it, right? So A has 4 bits, so A3, A2, A1, A0, right? So how many possibilities you can have? 2 power 4 possibilities. So B is also 4 bits, so B3, B2, B1, B0. Again, how many binary strings of length 4 you can have? 2 power 4, right? Both of them are being sent to a 4-bit comparator. Right, so what are the total possibilities of inputs? 16 cross 16, which is 256. There are 256 possible inputs to your 4-bit comparator. Right, so the question says, how many of these computations for which A is less than B? Right, so notice that, look at this. So out of these 256 possible pairs of inputs, let me write it as 256 pairs of inputs, right? When all can A be equals to B? So for any A that you pick, right? See, the moment if you want A equals to B, you can pick 2 power 4 possibilities for A, and the moment you pick 16 possibilities for A, B is also fixed, right? So there are 16 possible pairs. There is a total of 16 pairs where A equals to B out of these 256. So we are now left with 240 more pairs. So when A equals to B, A can't be less than B, because this question says how many possible combinations are there where A is less than B. Now, out of these 240 combinations, okay, the logic here, the small logic here is 50% of the cases A will be less than B, and 50% of the cases A will be greater than B. Now, you might say why? Again, that's very simple. Imagine if I take A as, let's say, 0000, B as 0001. For any pair that I take like this, where A is less than B, if I just swap these values, if I make A equals to 0001 and B equals to 0000, if I just swap these values, so for any pair that I place here, suppose there is one pair that I place here, if I just swap these values, that pair now will go into this side of the tree. So these 240, I can break them into 2 disjoint sets using this simple mechanism, where 50% will fall in this set and other 50% will fall in this set. And for every pair here, you have an exactly equivalent pair where A and B values are swapped. Right, so out of this 240, 120 pairs will come here, 120 pairs will come here. So the answer here is 120. Very simple question actually. Okay. Again, this is a, I mean, it's an interesting question. Okay. Cool. Let's go to more interesting questions. This is also easy actually. Again, if this column is correct, then it is option A. If this column is correct, this is option B. If this column is correct, option C. If this column is correct, option D. Okay. Because I couldn't draw 4 tables in one screen. That's why I've drawn it as columns. Again, QN stands for Q next. Again, you have to pick this column. You have to pick answer as A if this column is correct. You have to pick this column. You have to pick B if this column is correct. You have to pick C if this column is correct. D if this column is correct. Again, please be careful here. It's very easy to do silly mistakes if you're not careful with this. This is an easy question. You can expect this type of question for 1 mark. Okay, yeah, so most of you are getting the right answer here. Again, it's very simple. So if you draw here, I mean, there are many ways of solving it. This is a more thorough way of doing it. You have A, B, Q, and you have Q next, right? What is your Q next? Your Q next is A dash Q dash plus B dash Q, right? So what are all the possibilities that you can have here? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, right? You have to just apply this formula, right? If you just apply Q next based on A, B and Q, you can write the formula for this, right? So this will give you 1, this will give you 1, this will give you 1, this will give you 0, this will give you 0, this will give you 1, this will give you 0 and 0, right? If you can draw this problem is trivial and straightforward, right? So let's see. So when A equals to 0 and B equals to 0, what is happening here? This is being, see, look at this. Whatever your Q is doesn't matter. When A equals to 0 and B equals to 0, your Q next is always set. Simple question, right? So when A equals to 0 and B equals to 0, it is always set. So this can't be the answer. So eliminate this. Eliminate this. You're done. You're left with only 2 options now. Now when A equals to 0 and B equals to 1, look at what's happening. What happens to Qn given Q? Q is complemented here. Q is also complemented here. So what is happening here is when A equals to 0 and B equals to 1, what is happening is the Q is getting complemented when you have to arrive at Q next. So the operation that's happening here is complement and not retain. So option C is the right answer, right? Again, you don't have to draw this whole thing. You can start from here. Start looking for 0, 0. That helped you eliminate this column and this column. Just do for 0, 1, 0, 1. That helps you eliminate, that helps you eliminate column D also. You'll be left with column C, which is the answer. Fairly simple problem actually, right? Okay, Okay, here comes an interesting question. This is also easy actually. If again, we have solved similar types of problems in the course videos. So this should be easy. So here repeats means the sequence will repeat. That's what it means. Again, most digital logic design questions are typically easy except for a couple of variations. We'll come to those couple of variations in the 9th and 10th problem that we have. Those are slightly tricky. So we'll come to the 9th and 10th question. They're not hard, they're just slightly tricky. So this is an easy question. Again, for those of you who have seen course videos, we've discussed some very similar problems in the course videos. This is simple, guys. It just requires, if you know how to design a sequence of outputs using flip-flops, intuitively you can solve it. You don't have to design the whole solution here. Because GATE is not a subjective paper. Imagine if this was a subjective paper, you could be asked to design the actual flip-flop which generates this. That will be fun. But GATE cannot ask that question because it's not a subjective paper. It's asking for the minimum number of flip-flops. Okay, most of you are choosing between these two options, 4 or 5. So let me argue why the answer is 4. Okay, so the question says minimum number of flip-flops required to generate the following sequence. Right, so first and foremost, look at this. There are 4 distinct values here. So to store 4 distinct values, you need 2 bits. Okay, I'll also explain why some people think 5 is the answer. I'll just explain that, right? So to store 4 distinct values, okay, to store 4 distinct values, you need 2 bits intuitively. But the 4 itself has 4 positions. Look at this. This has 4 positions. This has 3 positions. This has 2 positions. This has 1 position. So the maximum number of positions that you have to keep track of is 2 positions. Okay, so there are 4, so unique 4 values, and there are 4 positions. To store where you are in these positions, you need 2 more bits, right? So this results in 4 bits as the answer. Now, some of you may say, hey, how is that possible? You actually need 5 bits because a flip-flop that generates 4, right? Because 4 requires 3 bits to be generated, right? Think about it. If you want to actually generate a value 4, you need 3 bits, right? So some people may say, hey, even though there are only 4 unique values, to generate 4, we need 3 bits. Right? I agree with you that we need 2 bits for the position, but to generate 4, we need 3 bits. That's what some people might argue, right? So that's why they might say the answer is 5. But a counter argument to that is why we don't require 4 bits is, imagine I generate, using my flip-flop circuit, the minimum number of flip-flops that are required, that's all the question is. Imagine I generate, instead of generating 1, 2, 3, 4, imagine I generate 0, 1, 1, 2, 2, 2, 3, 3, 3, 3. Okay, let's assume the flip-flops output this output that they're generating. But what, imagine if I have a 2-bit flip-flop plus 2 bits for the 4 unique values and 2 bits for the position. So I can generate this sequence using this, using 4 flip-flops. Using 4 flip-flops, it's very trivial to see that I can generate this. Now on top of these flip-flops, I can just add +1 to each of them. Right? Any output that I get, I can just add +1 and generate the sequence that I want without using any more flip-flops. Right? I can create a very simple adder, simple increment circuit. I don't require a complex adder also. I just require a simple increment circuit, which given any number will increment it by 1. Right? So in this sort of solution, what do I have? I have only 4 flip-flops, but I have an increment circuit. And the question says minimum number of flip-flops required to generate this sequence. I'm able to generate this sequence using 4 flip-flops and one small circuit for an increment operator. I don't require all the 5 flip-flops. So one way this question could be Again, that's why the answer needs to be 4 and not 5. It's a very common confusion, right? So that's what is important here. Cool. So let's go to the 9th question. This is an interesting question. Please be careful while solving it. This question is very easy to make silly mistakes on. Folks, any of the general questions you have, feel free to email us and let's focus on solving the questions today. Again, please read the options very, very carefully, because this question, while it is actually easy, it's also very easy to make silly mistakes in. After this, we have one more question. Again, please be careful with this question. It's very easy to do silly mistakes on. So Subhash has a question on how to prioritize. Subhash, we have done a video which is available on YouTube, where we discuss about the order in which you should prepare so as to score maximum marks. Okay, so please check out that video on YouTube. I think it is called How to Score 50 Plus Marks in GATE. Okay, so where we clearly describe what subject questions are typically easy, what subjects you should prioritize, and things like that. So please check out that on our YouTube channel. It's already available. Okay, I see, wow, I see multiple answers here, which means people are doing mistakes. This problem is, it's not hard. It's slightly time taking, but it has a lot of pitfalls that you'll fall into. You'll easily make mistakes here. So be careful, please. Take your time, think through this carefully. There are many ways of solving this problem. I'll show you 2 ways when we get into it. There is an elaborate way of solving this. There is a way where you can try out each of the 4 options and eliminate them and get to an answer. Both ways are possible here. I'll give few more seconds because this is slightly lengthy if you're going through the detailed process. So let's take some more time so that everybody finishes this. Yeah. So hit and trail is basically means that you're eliminating options, right? That's another way of putting it. You can try all the 4 options and see which works, or by elimination. Okay, so let me explain step by step. So the first approach is to try out each of these options, right? So first thing here is j equals to x, so which means j equals to, this is j, k equals to y complement, right? So what does this imply? K equals to y complement basically means y equals to k dash, right? So if you want to make this k, then you have to complement all of them, 1, 0, 1, 0, right? So again, in jk, remember that j means set, j is equivalent to set, k is equivalent to reset. I always remember it like this, otherwise I'll mess it up. I do silly mistakes if I don't think that way. Except that unlike an SR flip-flop, JK flip-flop, when it is 1, 1, it toggles. That's how I remember concepts easily. Okay, so when you have set equals to 0 and reset equals to 1, this is giving you 1. That's not right, right? Look at this, in a JK flip-flop, if reset equals to 1, then it should become 0. So obviously this answer can't be right, right? So we have just eliminated one option here. So similarly, you can keep eliminating all the options. Okay, you can eliminate first option, try second option, third option. Let's go to the fourth option. Okay, so j equals to y dash and k equals to x. So this is your k, j equals to y dash, right? So which means if this has to be j, you have this all these should be complemented. So you complement it into 1, write it as complement, complement, and complement. Now what happens? Remember that j basically means set, k basically means reset. Okay, so now does this work? So we obviously eliminated 1. You can keep trying out 1, 2, 3, 4, all the options. So for fourth option, let's see what happens. Your j equals to 1, which means it will set. So this is working out all right. Okay, what is the next option? Both of them are 0. So nothing is changing. Qn plus 1 is same as Qn. Perfect, makes sense. Next, both of them are 1, which means it is complementing. Makes sense. The fourth option, look at this. This is 1, reset is 0, or k equals to 0. Then it should 0. So if you try out each of these options, you will eliminate 1, 2, 3, and you will be left with option 4. Okay, so that's one way of solving it. Another more detailed way of solving, if you have the patience for it, is, again, I assume that you know the excitation table for JK flip-flop, which means if you want to go from Qn as 0 to Qn as 0, what should J and K should be? This 5 basically means don't care. Okay, so this is a more detailed way of solving it. And again, we explain how this detailed way works in the course videos in a lot more detail when we design multiple circuits. So if you don't want to do the elimination based method, there is a lengthier process, okay, which is first write down the excitation table for JK flip-flop. Then for XYQ taking all the possible values, write what is the Qn plus 1 based on what is given to you. Based on what is given to you, write what is Qn plus 1. And if you want to go from this Qn to this Qn plus 1, what should J and K values be? Now try and represent J as a function of X and Y and Qn. Similarly, represent K as a function of XYQn. And how do you do that? You do that using K maps. Now, if you do that using K maps, you'll get K equals to X and J equals to Y dash. So this is a more lengthier way of solving the problem. Okay, this is certainly lengthier way, mostly takes more time. But for problems like these, since the options here are very simple, right, you can just substitute and eliminate and eventually get the answer quickly. But you have to be careful when you're applying them. I see a lot of people answering A because they have probably made a silly mistake. Okay. Cool. So let's go to the 10th question. Okay, this is one second, guys. Just give me a second. How do I? Okay, I'll have to reduce the size of this because I set it to a slightly different size when I started the session. Just give me a second. View full screen. Okay, let me move this aside. Okay, I hope everybody can see this now. Okay, let me see the chat window quickly. Again, please be very careful with this question. I mean, I love these types of questions. They're fun. Okay, this is slightly messed up. Again, there is a sentence here. The arrow. Come on. 1 second, guys. Just give me a second. I'll edit this because I changed the size of the. Just give me a second. So this whole thing is going for a toss now. I'll just edit the structure here. Just give me a second. Just give me a sec. Okay, I should not have edited the, because some of you have asked for me. Just placing it correctly is sometimes tricky. 1 second. Just let me place it correctly. Give me a second. Or else let me put it at the very top. Okay, probably this is better. View full screen. Come on, the options are getting messed up. View full screen. Just give me a second, guys. Okay, so now everybody can see the question, right? Let me dismiss it. Okay, cool. Yeah, now everybody can see I just pulled the diagram above. Sorry, since I went from 100% to other size, now you can take your time and solve it peacefully. So Subhash says he has covered through all the concepts but not practiced. Subhash, that's not very helpful, to be honest with you. Please solve as many problems as you can. Go through the order of subjects that we have mentioned. We have given also a syllabus, if you recall. We have a live session on that, on how to score 50 plus marks in GATE. Go through that order, solve as many problems. If you don't solve problems, you cannot crack GATE. Let's be realistic there. Okay, so please solve problems. Again, anybody who has a question, who is a registered enrolled student, we try to first answer using email or audio messages, in some cases even video messages. If that is not resolved, then we set up a call, right? So we always first try to resolve your questions over email, because we can give far more detailed answer in an email. Because in a phone call, what happens is it's hard to show you diagrams, right? So we prefer email, audio. There are cases where we give audio answers also, some cases where we give video answers also. But in an email, we can explain the solution in much more detail. Phone calls are always an option that we use in case nothing works, in case your question is not resolved. Again, if you have a specific issue, please do reach out to us. We'll help you through that. If you're a course enrolled student, obviously we'll try to ensure that your questions are given higher priority. It could be any question. It could be general question. It could be conceptual question. It could be about practice, anything like that. Again, please be careful with this. You have to be really, really careful. So just for clarity, this is also CLK, clock. Okay, some people say C, some people say D. Again, this question is designed to ensure that you understand how to think about a flip-flop based circuit and how it goes from one state to other state. If you know how to handle that, this is actually an easy question. Mayank, thank you for the appreciation to Subbarao. He's one of our very patient and very dedicated teachers. He's one of the many people for sure. He's also one of our first people who joined us as a mentor and instructor. A phenomenal guy. Yes, his patience is immeasurable. I mean, he has enormous patience to talk to students and clarify their stuff. Yes. Again, that same patience and student centricity you can find amongst many of our mentors, almost all of our mentors. Again, the sequence is Q1, Q0. Somebody has this question, Jones Anthony. So the sequence that you should look for is Q1, Q0. Okay. The question says they want the sequence Q1, Q0, not Q0, Q1. Okay, some people even say B. Okay, so let me try to answer this. We'll go step by step. Oh, somebody says even A. So initially, look at this, Q0 and Q1 both are 0. So this is 0, this is 0. It's very simple to analyze circuits like this. If you're careful, we have to be careful here, right? Look at this. This is a positive, so this is an edge triggered positive clock signal or positive edge triggered. This is also positive edge triggered, right? So this is 0, this is 0. Now let's see what happens. Okay, so this 0 will feed into this circuit, this 0 will feed into this circuit. So 0, 0, this is so AND gate is 0, NAND gate is 1. So this becomes 1 now. Look at this becomes 1. This 1 is fed in now. Okay, so the moment this 1 is fed in, this is a D flip-flop. Remember, this is a D flip-flop, this is a T flip-flop. D flip-flop will pass, whatever is here, it will pass here as soon as it gets an edge trigger, right? So what will happen here? This 1 will be passed here. This one will be passed as soon as you have a trigger here. This one from the input goes to the output. So this 0 becomes 1 now. Now look at this. This 0 became 1. So what happens? Look at this. You went from 0 to 1. Okay, that creates an edge trigger. That creates a positive edge trigger. So the moment this output goes from 0 to 1, because this output is connected to the clock, this gets activated. Okay, because again, remember, this is a positive edge triggered clock, a positive edge triggered circuit, right? So again, so the moment this circuit becomes active, what is the input to this? The input to this is 1. The moment you have 1, again, remember, this is a toggle flip-flop. What does a toggle flip-flop do? Toggle flip-flop toggles whatever was the previous state, right? So this is 1. So this 1 will go here, right? So this will toggle. So this will make this 1 now. Okay, so remember the initial state is 0. Initially both the bits, let's write Q1, Q0 bits. Okay, Q1, Q0 bits initially are 0, 0. What is the next state? That's what we are trying to figure out, right? Now all this, so we just had one clock trigger. We just had one edge triggered clock here. With that, all these changes are happening, right? As soon as this triggered, this 1 went in, this 1 became the output, and here it went from 0 to 1. So this clock also has an edge trigger. So this will toggle. It was initially 0. It will become 1 now. So this 1 will go as an input here. Look at this. This 1 will go as an input here. So 1, 1, what happens to NAND gate? Look at this. What happens to NAND gate now? Your NAND gate now is, giving you 1, 1 is 0. Right? 1, 1 is 1. AND gate is 1. NAND gate is 0. But remember, very, very importantly, at this point, you have not got the second edge trigger clock here, right? You have not got the second trigger. So this 0 is there, but this 0 will be passed on here. This 0 will be passed on only to the next trigger, not to this trigger, right? This 0 will be passed on only to the next trigger. So for the first clock trigger, that you had, or the first edge triggered clock that you had, you went from 0, 0 to Q1, Q0 as 1, 1. Look at this, you went from 0, 0 to 1, 1. Next you will get one more edge trigger here, and with that edge trigger, this will become output, and so on and so forth. Right? The first thing that you have to see here is we went from 0 to 3 here. Right? All this happened, the most important thing here is all this happened with just one edge trigger clock here. With one clock signal, initially we were 0, we went to 3. Now if you notice, this can't be the answer, this can't be the answer, this can't be the answer, because after 0 you have 3 here. The only possibility is this, right? So that way you don't have to do this multiple times, right? You don't have to do this multiple times. So by just looking at it twice, you can easily eliminate these 3 options and you have 3. Okay, that's how simple it is. Remember that the most important thing, you have to keep changing these states very, very carefully, as I've just shown you. It's very important you do that, and also make sure you do it for each trigger from the clock. Here this clock triggers, again this clock will only trigger when you go from 0 to 1. So when we went from 0 to 1, this clock triggers, right? When this clock triggers, whatever, because this is a toggle flip-flop, whatever was the initial value, it becomes 1, right? So you have to be very, very careful when you're analyzing these types of flip-flops, but with some practice it's actually very easy. Okay, those of you who are course participants, we have solved similar problems very much more complex than this actually in the course videos, right? So thank you very much for joining. These were the 10 questions we had. Again, please understand that DLD is about 6 to 7 marks on an average. Very easy to score if you practice, and it's already 8:04. So tomorrow we'll do the general Q&A session. Again, we'll try to answer as many questions as possible. Our mentors also will be there. Any question that I may not be able to answer, it's impossible for me to know everything. Our mentors also will try to answer some of the questions. Okay, see you tomorrow at 7 p.m. and stay safe and a happy weekend. Okay, see you tomorrow. Bye-bye.